Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who recognized and selected CSI Training as the world leader for quality instructional products. The next 40 minutes will reveal the keys to successful alignment. Whether your alignment system is mechanical, electromechanical, or laser, you will be able to apply the tips and techniques presented here to strengthen your abilities and confidence to perform precision alignment and enhance your reliability-based maintenance program. We will briefly consider the diagnosis of misalignment using spectral and waveform data, as well as the steps to detect and correct soft foot condition, piping strain, and coupling runout. Precise steps are shown to use reverse dial indicator, electromechanical, and laser systems to achieve a quality alignment and be within tolerances to increase the machine's life and decrease maintenance costs. Let's look at the characteristics of misalignment to see the effects on a machine and how they will show up in spectral and waveform data. When two shafts are aligned, their center lines will be a straight line from the end of one shaft through the end of the other. This common center line is called a common collinear axis. Misalignment, then, is any condition where the shaft center lines are not in a straight line during normal operating conditions. One common type of misalignment is angular misalignment. The two shaft center lines meet, but they meet at an angle. The shafts could be at an angle horizontally or vertically, but it's typically a combination of the two. The second type of misalignment is offset or parallel misalignment. The shafts are parallel, but the center lines of the shaft don't match up. In fact, the shaft center lines never cross as they do in angular misalignment. Although angular misalignment and offset misalignment are sometimes referred to as coupling misalignment, we are actually aligning the shaft center lines. When the machine is running in an angular misalignment condition, the two shafts are tied together with a coupling that forces the ends of the two shafts into better alignment. This pulls on the shafts and produces movement and distortion of the shaft as they attempt to align themselves. The shafts are forced in the axial direction once during each shaft revolution, and they move radially as they are pulled by the coupling. In spectral data, then, we expect to see a peak at the shaft turning speed in the axial direction. The radial directions, both horizontally and vertically, will also have a peak at shaft turning speed. With offset misalignment, the shaft tends to move or bump a sensor 2 times during each shaft revolution in the radial directions. However, there is very little movement in the axial direction. In the real world, though, there is usually a combination of angular and offset misalignment combining the responses. Both angular misalignment and offset misalignment produce repetitive vibration, which will be indicated in the waveform data with a very repeatable pattern. In these examples, we have looked at angular and offset misalignment in their purest sense, without regard to the effects of various coupling types, machine characteristics, and so on. In reality, various coupling types produce different responses in spectral and waveform data. In tests performed by CSI, a machine was aligned and misaligned with exact amounts of purely angular or purely offset misalignment and repeated for 5 coupling types. Each setting was run under load and vibration measurements were made. The results varied for the couplings. The 3-jaw coupling showed the most vibration at 3 times shaft turning speed, with multiples appearing in severe misalignment conditions. The bun or rubber tire type coupling and the rubber gear coupling had high 2 times shaft turning speed peaks in the radial direction. The shim pack coupling had peaks at both 2 and 6 times shaft turning speed. The grid type coupling had a high 4 times turning speed peak. Because the various couplings produce different responses, it is important to know the flexible coupling type for a more accurate diagnosis of the alignment condition. Sometimes we are asked, why worry about misalignment? Isn't all I need a good flexible coupling? John Piotrowski answers this in his book, Shaft Alignment Handbook, where he points out that coupling manufacturers will often quote information on allowable misalignment for the coupling and not the equipment to which it is coupled. These tolerances seem to lull the user into a sense of complacency, leading one to believe that accurate shaft alignment is not necessary because the coupling can take care of any misalignment. Although the coupling may be able to handle these stresses, the mechanical seals, bearings, wear rings, and so forth cannot. The stress created by the misalignment is still passed on to these components, causing premature failure. So it is necessary to be concerned with misalignment. In contrast, a machine in good alignment condition extends the life of the bearings, mechanical seals, the couplings, wear rings, and the shafts, as well as reducing vibration and minimizing shaft bending and cyclic fatigue. Quality alignment is proactive and removes the root cause of failures due to the forces of misalignment. In fact, studies have shown that machines properly aligned can reduce electrical power consumption by at least 4 to 9%. Misaligned conditions can be detected using at least 5 predictive maintenance methods that do not require an interruption of the process. They are spectral and waveform analysis of vibration data, as was shown earlier, phase analysis of vibration data. Another is to measure coupling and shaft temperatures using an infrared temperature probe or infrared thermography. And the strobe light can be used to actually see shaft, coupling, or machinery movement in slow motion. Because phase is the relationship between 2 points, it can be used to determine how a machine moves compared to a marked point on the shaft. Mark the shaft with reflective tape for the shaft reference, and use an infrared phototac to pick up a signal each time the shaft turns. This is the constant, while the vibration sensor is our variable, that is, it will be moved from one position to another, and the relationship between the phototac and the peak of vibration can be measured. Monitor the horizontal bearing location on one side of the coupling and read the phase angle. When this phase reading is compared to the one across the coupling, we can determine how the machine is moving. If the phase readings are about the same, then both sides of the coupling are moving together or in phase. However, when there is approximately a 180-degree difference in the phase readings, one component of the machine is moving one direction, while the other component is moving the opposite direction or out of phase. This is characteristic of misalignment conditions when the 3-jaw coupling, the shim-pack coupling, or the bun-type coupling is used. The grid coupling and the internal gear coupling typically don't follow this pattern. Peak and phase readings made in the axial direction across the coupling can also be used to detect a misalignment condition. Readings approximately 180 degrees apart mean the machines are moving opposite each other and indicate angular misalignment. All of these rules of thumb are based on the sensor being turned the same direction for comparative measurements. The readings will change 180 degrees when the sensor is turned around. The forces of misalignment cause flexing and movement of the shaft and coupling and generate heat. This heat can be measured while the machine is running to determine the presence of misalignment. In another video program, Introduction to Infrared Thermography, we showed examples of thermographic images from tests with various couplings and misaligned conditions. Some of the coupling temperatures from an aligned condition to a misaligned condition increase by as much as 65 degrees Fahrenheit. The movement of the coupling due to a misaligned condition can sometimes be seen in slow motion when a strobe light is flashed close to the rate of the shaft turning speed. All of these methods can be used to detect misalignment, but other symptoms of misalignment are apparent without the aid of tools or instruments. Some of these symptoms are excessive oil leakage, powdered rubber under couplings that use rubber inserts, leaking seals on pumps, soft foot condition, broken foot bolts, oil shimmering under the machine foot or base plate, and premature failure of bearings, seals, shafts, and couplings. The benefits of precision alignment far outweigh the costs, and the price of poor alignment is much higher in the long run than it first seems. There are many methods for proper shaft alignment, and they're illustrated in the next section. If you were to hire a contractor to align a machine, would you get better alignment from a dial indicator set that costs a few $100s, or a laser set that costs tens of thousands of dollars? The key to remember is, tools do not align machines, people do. The tools are merely used to measure the alignment condition, and some tools help calculate the machine moves. But the better tools help a competent person to perform the same job faster and with less risk of error. Some tools and alignment methods were never intended as the final alignment, but in industry they've often been used as the final fix. Two brothers, Bo and Boo, illustrate this well.
Bo, how do you do alignment on pumps and motors?
Use the old eyeball and shim it.
That's all. Is there any other way?
When I want to get it close, I use a straight edge and a flashlight.
The straight edge and flashlight method was only intended for a rough alignment during installation and is the least accurate method of alignment. The straight edge is used for the offset misalignment and a taper wedge or feeler gauge for the angular position of the shaft. However, it can only work on certain couplings, and because it does not require special tools, it is often used as the only alignment step before returning a machine to service. When only one shaft can be rotated, the face rim method can be employed, which uses a dial indicator on the coupling face to measure angular misalignment and a dial indicator on the rim to measure the offset misalignment. The dial indicator readings are then graphically or mathematically projected to the machine feet to determine the required adjustment and shimming for each foot. A dial indicator has a spring-loaded plunger in the back which turns the needle in the face as it is moved in or out. The dial indicator is positioned near a part of the machine so that the pin is pushed about halfway in. The face of the dial rotates, so this position can be marked as 0. As the shaft is turned, the tip riding on it changes the dial reading with any change in the relative position of the shaft. When the plunger is pushed further in, the needle moves in the positive direction. When the plunger moves farther out from the dial, the needle moves in a negative direction. Most dial indicators are designed to measure in mils. 1 mil equals 1/1000th of an inch. The face rim method works well for short spans, and it is easier to visualize the readings. The disadvantages are that it easily becomes a trial and error process. Any axial shaft float will induce error in the face reading and affect the angular misalignment calculations, since this face reading is used to determine the amount of angular misalignment. When using the face rim method, it is critical that the coupling is true. Often couplings may be bored off-center or at an angle, which then causes the outer rim and face to be eccentric or have runout. Since the corrections for misalignment are based on these surface measurements, only a trued coupling will produce adequate results. The reverse dial indicator method is used when both shafts can be rotated together. A dial indicator is mounted on each shaft, and the dial is actually measuring across the coupling to record the relative movement of the opposite shaft. These measurements are then mathematically or graphically projected to the machinery feet, where corrections are then calculated for adjustments and shimming the feet. This method can be used for longer spans than the face rim method, and because the shafts turn together, it is independent of coupling runout. Axial movement does not affect the measurements, because the dial indicators do not measure in the axial direction. However, if the coupling has any torsional shift as the shaft is rotated, then error will be induced into the reading, and the bar holding the dial will have some amount of sag that needs to be compensated for. The reverse dial indicator method can be simplified with electronics, such as this CSI Model 8110, which uses a patented method to automatically compensate for bar or bracket sag. The principal difference between the reverse dial indicator method and the electromechanical system is the dials are replaced with digital heads that make the readings and transfer the data into an alignment analyzer, which calculates the machine moves and required shims under each foot. Although the electromechanical system is more costly, the calculated moves reduce time and minimize the error factor, saving manpower and downtime dollars. Bar sag or bracket sag is not a problem with a two-head or dual beam laser system, which emulate the reverse dial method and mounts laser beam heads in place of the dial indicators. Each head sends a laser beam and receives one from the opposite head. The change in position of the beam on the receiver is tracked as the shaft rotates, and the information is then sent to a receiver on the alignment analyzer. This wireless system is the most precise of all the systems, Because there is no bracket sag, it is unaffected by coupling runout and any axial float in the machine. The laser system can be used over longer spans than the reverse dial method, but its accuracy can be affected by airborne particles. When an alignment analyzer is not available, the machine moves must be determined by graph or mathematical equation. Whatever method you use, there are common steps that must be completed before actually performing the alignment procedures. These are explained in the next section. The alignment process involves 7 steps that must be performed to ensure personnel safety and successful alignment. First is the pre-shutdown preparation that facilitates a faster, thorough job. Then shut the machine down. And the third step is a series of pre-alignment checks. Then the misalignment measurements can be made. Next, reposition the machine and repeat the measurements. Repeat these steps until the misalignment is well within tolerances. Restart the machine, and after the unit has returned to operating conditions, recheck the data used to calculate offline to online conditions. Before shutting down the machine, take the time to perform these 4 steps, and you will decrease the time for the actual alignment. First, obtain all the tools and measurement devices. Include the alignment fixtures and mounting tools, whether mechanical, electromechanical, or laser. Get the dial or digital indicators, magnetic stands, a good 1-inch outside micrometer with at least a 1 mil resolution, feeler gauges 3.5-inch and 6-inch long, measuring tape, pre-cut stainless steel shims of appropriate size, brass or stainless steel shim stock, tin snips, small hammer, needle nose pliers, a plumb bob, an extension mirror, chain or strap wrenches, automatic center punch, and a permanent marker. Be sure to include the tools needed to remove the coupling guard, loosen the feet, and move the machine, including wrenches, jack bolts, and hydraulic jacks. Remember to include the vibration analyzer for before and after data, and a device to measure the machine temperature, whether it is an infrared thermography system or a temperature sensor. Collect vibration data and other operating data. Be sure to collect the necessary data to determine the online to offline running condition. Inspect the base plate, foundation, grout, and hold downs. Notify operations and follow all safety procedures to shut down and lock out the machine. The online temperature data will be used later to help you determine thermal growth. Thermal growth is the change in the physical size of the machine from the offline condition to the online condition. If thermal growth is not taken into consideration during the alignment process, the smooth running condition and restart may become a rough, vibrating machine when it returns to its normal operating temperatures. Most machinery operates well above ambient temperatures, and the actual size of the machine will increase as the temperature increases. This would not be a problem if the machine grew the same throughout, but that is seldom the case. Instead, the fan end of the motor will typically be cooler than the coupling end and therefore not grow as much. If the driven unit is a pump and it is transferring a hot solution, it could grow more than the motor, increasing the misalignment. On the other hand, if the pump is pumping a cold solution, it will actually shrink smaller than it is at ambient temperature. This thermal growth will affect your alignment results and, if neglected, could lead to machinery failure. There are several tools and methods to measure thermal growth, such as Essinger bars and Don bars, that are used for measurements at both running and ambient conditions. One technique to estimate vertical growth does not use special tools except a temperature probe. The temperature is recorded in at least 4 positions in a line from the foot to the center line of the shaft, and is measured for each foot and bearing location on the machine. Temperatures are recorded for both the online and offline conditions, and their differences are averaged to a single number at each bearing location. The amount of expansion is then calculated using the formula E equals T times L times C, where E is the expansion in mils, T is the temperature in degrees Fahrenheit, L is the length of a vertical line from the center of the shaft to the shim plane, and C is the coefficient of thermal expansion in mils per inch degrees Fahrenheit. The coefficients differ from material to material as shown here. The coefficients all seem to be very small numbers, but notice that aluminum is twice that of cast iron. This means that if a motor housing is aluminum and is coupled to a cast iron pump, the motor could actually grow twice as much as the pump with the same temperature increase. The temperature measurements and calculations must be made at each bearing location. These numbers are the expected amount of growth in mils when the unit is returned to normal operating condition, and this growth must be compensated for when determining the amount to shim each foot. After the machine is shut off and locked out, there are 7 checks that must be made before any misalignment measurements can be performed. Some of these may require additional corrective work, but will assure successful alignment. Remove the coupling guard and inspect all accessible rotating parts. If the coupling has a rubber insert, check for rubber powder, because this is an indicator of the amount of misalignment, and a worn rubber insert can allow too much looseness in the coupling, accelerating the wear and increasing the vibration. On lubricated couplings, check for leaking grease as an indicator of wear or looseness. Check the keyway for wear and a loose key as an indicator of a loose coupling. Check the coupling for tightness and any play between coupling halves, including movement in the axial direction. Loosen the foot bolts and clean the top and bottom of the machine feet and the base plate, checking for any burrs or rough surface. A heavy-duty cleaning agent will help loosen and remove any residue. Check the foundation for cracking and loose grout. If the base plate has several coats of paint or is rough, it should be machined to a smooth surface. Check the condition of any existing shims, cleaning them and inspecting for burrs or rough surfaces. Discard any distorted, rusty, or aluminum shims. Verify the thickness of shims over 25 mils thick with a good outside micrometer that has a resolution of at least 1 mil. The shim should be the same thickness throughout. Mark the thickness on the good ones and record the thickness that was under each foot. There should be no more than 5 shims under any foot at the same time, because the stiffness of the foot decreases as the number of shims increases. If several shims are to be used on a foot, sandwich the thinner shims between the thicker ones. Measure shaft runout for a bent shaft condition and measure the runout on the coupling. To set up for measuring the shaft and coupling runout, mount